Good morning, everyone. Welcome to our Bangalore Theory Seminar. Today, we have with us Anay Mehrotra. Anay is a PhD candidate at Yale University, advised by Amin Karbasi and Manolis Sampetakis. His work deals with developing and applying learning theoretic tools to missing data problems arising in a bunch of areas like causal inference and fairness. His recent work has received the Cold Best Paper Award, and on which I believe he'll be speaking today. So, without further ado, let's welcome Anay, and I'll hand it over to him.
Thank you. Can you hear me? Okay. Hi, welcome everyone. Yes, I'll be talking about learning theory's applications to identifying treatment effects from observational studies. I'll define these terms in a bit. And this is joint work with Yang Sai, Alkis Kalavasis, Katerina Mamali, and Manolis Empetakis. All of us are from Yale. Okay. So let's begin by defining what an observational study is. In an observational study, you observe individuals, and these individuals have different features that divide them into groups. So here, the individuals are divided into two groups, one of young people and the other of old people. So the feature is age. Each individual in an observational study also has a treatment assignment, for instance, whether they smoke or they do not. This is the standard terminology, but it's kind of ironic that I'll be using treatment to refer to smoking. And unlike a randomized control trial, in an observational study, these treatment assignments are chosen by individuals. So they are not in particular randomized. They can depend on all the underlying features you see as well as features you may not see. Okay. So for instance, here the assignment isn't quite random. Older people are slightly more likely to smoke than younger people. Okay. So apart from features and treatments, individuals also have outcomes such as whether they're healthy or unhealthy. And our goal is to understand what is the treatment's effect on the outcome. So let's say whether smoking makes an individual less healthy. Okay. So outcomes would be like bounded real numbers for us. They don't need to be binary. Okay. And there are many ways of measuring the effect of a treatment on the outcomes. And a standard metric here is the average treatment effect, which is defined as the average difference in the average outcomes in two extreme worlds. In one world where everyone decides to smoke, and in the other world where no one decides to smoke. We will focus on the average treatment effect throughout this talk, but the techniques in this work also extend to other types of treatment effects, and so enable use of some learning theoretic tools for understanding other treatment effects as well. Yeah. So before proceeding to our results and existing work, let's try to understand why this problem is non-trivial. Okay, so consider an observational study where there are some individuals, some of them smoke, and our goal is to determine what's the average treatment effect. A naive way for estimating this is to divide the individuals into two halves. One, the set of individuals who smoke, and other, the set of individuals who don't smoke. So here you'll see that 1 in 3 people who smoke are. That expectation? Yeah, the top one? Yeah. Oh, okay. I'll go back. So this, I assume that there is some underlying distribution of covariates or individuals in my population, and the expectation is over them. For the individuals from the population. From the population, but it's not a finite set, like it's some distribution. Okay, and I guess the challenge is that you want to compute this expectation, but you only see one of these y's, right, for each individual, it's not both. So that's the thing I'm trying to describe here. So a naive way would be to just compute the average, but over the population you see, and using the y's you see. Yeah. So here, if you look at the set of people who smoke, two are unhealthy, one is healthy. So the expected number of people who remain healthy is 1/3. And on the other side, 2/6 remain healthy. So it seems like smoking doesn't really, like, at least if we believe this naive estimate, then smoking doesn't really cause any effect on health of individuals. But this is the wrong approach to take. It's a biased estimate. So what we should really be estimating is the expected value in these like two extremes. And you should really imagine these as random draws instead of a finite set. And once you look at this, now like only 1 in 9 people remain healthy when they smoke, whereas like many more remain healthy when they do not smoke, right? So this is like, I guess I want to pause here to like stress on this distinction. In this problem, like even if I give you infinitely many samples, it's unclear whether you can solve the estimation task that's been given to you. And this is different than more traditional, let's say, prediction tasks, where if you have infinite data, you can find the best fitting classifier. Right? You might not be able to classify all individuals, but you can find the best fitting classifier, and that's the goal. Here, even achieving that kind of a goal is unclear. Okay, so yeah, it's a long talk. I'll go over our work proofs, but I'll quickly summarize the takeaways. So to enable identification of what the average treatment effect is, existing literature in causal inference proposes several sufficient conditions under which you can solve the problem. The first contribution of our work is to take a more learning theoretic or computer sciencey perspective and try to characterize exactly when we can solve these problems. So we want necessary and sufficient conditions. And this characterization is particularly useful because the sufficient conditions people have come up with are easy to violate. And I'll give some examples of these conditions and why they can be violated. And in fact, the reason or the fact that they can be violated has led people to develop various relaxations of these conditions, which are no longer sufficient to estimate the average treatment effect, but you can get an interval in which the average treatment effect lies. So you cannot nail down the value, but you can get a range. And like a corollary for a result is in many of these frameworks, so not all, but in many of these frameworks, you can exactly identify the average treatment effects using some of these techniques. Okay, so in this sense, like this characterization acts as some bridge between everything we know in learning theory and CS and causal inference. Because once you know that it's identifiable, you can use many of the techniques to actually estimate the average treatment effect. Okay, so let's go into and try to understand what some of these sufficient conditions are. There are many more out there, but these are the main two. Okay, so one of the main problems in identifying the average treatment effect was that the decision whether an individual decides to take up a treatment or not was not randomized. So the first assumption people make is unconfoundedness, where I divide people into different clusters based on their covariates. And I say that in each cluster, the thing like my observational studies behaves like a randomized control trial. So if I have two groups of individuals, like young and old, then in the first group, there is some coin flip with some probability that decides whether they take up smoking or not. And in the other group, there is some other coin flip with some other probability which decides whether they take up smoking or not. Yeah. If these probabilities were the same, then you would have a randomized control trial overall. But the fact that these probabilities can be different for each group, like says that the overall thing is not randomized. It depends somehow on the covariates, right? Older people here are more likely to take up smoking than not because the probability is 2/3 there, 1/2. Yeah.
And there is no way to know this probability, right, from the observed data.
If you make this assumption, then there is. Because if you make this assumption that everything behaves like a there's no way to test this assumption. But if you make this assumption, then there is a way to test the probability. Because you can just take the expected number of old people who smoke, and that's a Bernoulli random variable, and you get a good estimate of the probability. Yes.
So is the assumption that there exists a cluster, or the clusters that we have that they are?
Yeah, the assumption is that you know the cluster as well. But there are two assumptions happening. Like there exists a cluster, and the assignment is really random in there, and that really random part is like not testable. And okay. The second assumption is that each of these groups in these clusters are non-empty. Okay. So here the group of young people violates this assumption. And like non-empty in the sense that we have individuals on both sides of the treatment. So here the group of young people violates this assumption because we have people who smoke, but we don't have anyone who does not. Oh, sorry, we have people who do not smoke, but we don't have anyone who smokes. Whereas the group of old people satisfies the assumption because we have people on both sides of the treatment assignment. Okay. Yes. Okay.
Saying there exists some clusters.
Okay, so the question is that if we make the assumption that there exists some clustering, instead of assuming that we know the clustering, does that add anything at all? There's a subtle answer to it. And the subtle answer is that if your clusters are defined by some covariates, if you have all the covariates that define the clustering, then yes, that assumption adds something. So let's say if I go back, here these two clusters, okay, this will come up in just the next slide, so maybe I'll stop and explain it here. Okay, so there are many reasons why these assumptions can be violated, and one of these is like the one I'm going to say. So one of the reasons, let's first talk about unconfoundedness, this assumption that each cluster behaves like a randomized control trial. And this can be violated if you have some covariates that you have not seen or some features, X's that you haven't seen that affect both and propensity of an individual to take up treatment as well as their outcomes. Okay? So in our running example, imagine the socioeconomic status of an individual that affects how likely they are to smoke if you just look at the data. And it also affects their access to healthcare. So affects like their outcomes. Okay. So now if there's a clustering that involves the socioeconomic status, then, and we don't observe the socioeconomic status, we never recorded it, then making the assumption does not add much. Okay. And like one corollary for work is that telling you how to sort of use it under some more assumptions. Right? If you have some willing to make some other assumptions, then even without having SES access, you can do something. But yeah, in general, you cannot. Okay, so one reason for violation of unconfoundedness is missing covariates, or what people call having latent confounders. So the natural thing to avoid this seems to be that like add as many features as we can, like observe as many things about the individuals and add it to your study. It has two downsides. One of the downsides is it doesn't come for free. Like if you add in something which people call a collider, which is a covariate which somehow is a like what is called a post-treatment effect. Let me not get into too much depth. Then it can like having too many things can also violate unconfoundedness, right? Okay. And then finally, like even randomized control trials where you're explicitly assigning randomized treatment to individuals, this should hold, but it can also be violated if participants decide to like not comply with your assignments, right? Sometimes if you're like have them in person, you can enforce these constraints, but when you want them to take up certain medication and people decide to drop out, it's a big problem in running RCTs. So like that's just to mention RCTs are not always immune to these issues either. Then let's turn to overlap, which was this assumption that each of our clusters, like we have had people on both sides of the treatment assignment. And there are some issues with ensuring this as well. Okay. So to address this problem of latent confounders, you try to add as many features as you can. Right now, if you added n features, each of them take 2 values, you have 2 to the n clusters. And now you want at least like 2 times 2 to the n individuals to see people on both sides of the aisle. So if you have too many covariates, then you expect overlap to be violated. Then there are some studies. I'll define these in a second, or actually not in a second, in a few slides, where overlap is just violated by design. Like these are studies where it's violated in an extreme sense. So imagine these are called the regression discontinuity designs. So imagine something like you're selecting students to join a university, and you want to understand whether joining the university made them earn higher, like after 5 years. Okay. Now, you might want to regress, like using technical terminology, on their score. So you perhaps expect people who scored similarly in high school to earn a similar amount, and now you want to see did going to university increase their income, right? As opposed to working for 5 years. But now there's an extreme regression discontinuity. There's this discontinuity at the threshold at which you select people to join the university. Presumably, once you start selecting, everybody would join and come to IISc to attend university. So if you look at people above that threshold, there is no one who did not attend university. If you look at people below that threshold, then by design, there is no one who could have come to IISc. Right, so there on both sides of the aisle, there is one person who didn't receive one side of the treatment, coming to university or not coming to. So these are type of studies where people make certain other like more assumptions to identify, and we'll see what we can do. And then finally, again, like if you're running randomized control trials, people decide to not participate or not follow your instructions, you can have problems with overlap. Any questions so far? Now I'll switch gears and try to get to what we do. Yeah, overlap is like where you have these clusters. You fix some clustering with respect to which unconfoundedness holds. And in each cluster, you want some people on both sides of like who smoke and who don't smoke. That's the definition. Okay, cool. So I'll try to get into a bit set up a notation a bit more. So like one of the ideas in our work is to factorize the data distribution in the right way. And this seems like some trivial thing, but it'll eventually play a crucial role in how we characterize things. Like factorizing this way somehow leads to an easier characterization than using some other factorization, right? And if there are people who are familiar with causal inference, this might seem like non-natural or different factorization than people typically do. So we have some distribution over features which are X, my outcomes which are Y, and treatment which I'll call T. And I factorize this into two parts. One is the feature outcome distribution, and the other is like what's the probability of getting a treatment given the feature and the outcome. Okay. This is what we are calling generalized propensity score. And typically in the second line, you don't have the outcomes. Because if you recall, like one of the issues was we don't see the outcomes. So there's no way you can compute the thing on the second line because you don't see Y for some individuals. You don't even know what their outcome is. Okay, but like formally writing down this notation will help us. So that's one of these things we do. And when you don't have a Y, people call it propensity score. That's why we are calling this generalized propensity scores. And now, like, yeah, I'll just introduce some more learning theory type or statistics type notation, which will help me like make the notation more succinct. So I'll say that my marginal of feature and outcome belongs to some class of distributions D, and my marginal of the generalized propensity scores belongs to some class P. And now I'll call my observational study distribution realizable if you know the corresponding marginals belong to the respective classes, right? So this is like if people assume Gaussianity, this is just saying that Gaussians are my class and my distribution is a Gaussian. But here there are some abstract classes. So in these terms, our goal is now to characterize the tuples P and D for which we can identify the average treatment effect. So this will tell us classes of P and D for which you can if you believe your observational studies is realizable by these classes, that you can solve the average treatment effect estimation problem. Okay. And for simplicity, throughout, I assume that these are continuous density and have continuous distributions and they have densities. Okay. So this is the main characterization, modulo some details. So the average treatment effect turns out to be identifiable if and only if like barring some mild conditions, which I'll explain when I get to the proof. And there is no pair of propensity scores and no pair of densities such that this ratio matches. Right? So if, in other words, if you have two classes P and D, and you construct new classes which take ratios of pairwise ratios, then these two classes must be distinct in some way. Okay. Yeah, I don't want you to get much from this, or I don't expect you to connect why this is enough or not enough, except that this is perhaps a simple enough condition that given some class, you can check it. Yes, so the dots mean like I take these ratios as functions. So I really do like P of xy by Q of xy, and that's a function of xy. So as functions, I want them to be different. And this is the identification result. So here, this really says that given infinitely many samples, or when I actually know the density, I can identify the average treatment effect. But once you have that, you can use like some more standard techniques in statistics to get quantitative results as well. So now if P and D satisfy this condition, and they have some nice like dimension. So for people familiar, let's say they have like the distribution set has a finite covering number, and the other class has something called the finite fat shattering dimension, like just like some regularity conditions, then we can estimate the average treatment effect with like finite samples. If you give me n samples, I'll get you an estimate which is like 1 by n close. Like I have a poly there, but it's like really like root n, the standard things you would expect. Okay. So before getting to the proof, let's go over the applications and how they look. And then at the very end, I'll go over the proof of the result. So the standard setting, which I described earlier, is where both unconfoundedness and overlap hold. And in this case, people already know how to identify and estimate the average treatment effect. So in this setting, our result just gives another proof of like the same result that was known earlier. But beyond this, we look at like three other settings where one or both of unconfoundedness and overlap are highlighted. I'll go over like scenarios 2 and 3 in a bit more detail next. In both of these scenarios, exactly one of unconfoundedness and overlap are violated. They're not so like we don't know how to estimate in general, but they're not so bad. Like not everything is violated here. And each of these turn out to be interesting for different reasons. So regression discontinuity designs, I already explained. These were cases where you have some extreme violation of overlap, but you have unconfoundedness. Uh, Unconfoundedness in a trivial way, where we assume that everyone above a score like attended university. So it's like a randomized assignment with probability 1 and a randomized assignment with probability 0 in the other way, where people below a score do not attend university at all. The other model where overlap exists but unconfoundedness is violated is what people call sensitivity analysis. And here the idea is, okay, what if unconfoundedness holds but not exactly, like it holds approximately. So it's violated, but I want to check the sensitivity of my estimate to this perturbation. Okay, and here I guess these can be applicable in any study you do. You might want to check the sensitivity of your results based on this assumption. But what is perhaps interesting is even when you have neither unconfoundedness nor overlap, there are some classes where you can still identify. I won't go over them in this talk because I don't know of any practical cases where that might be relevant. If you guys come up with some, that would be very, very interesting. But the other two, we have concrete studies like that at least fit the framework we are trying to capture. So with that, let's go over this first sensitivity analysis models. Okay. So I don't want you to parse the exact notation, except that like the thing in the middle is some function of this generalized propensity score. And this gamma is some parameter that captures how far you deviate from unconfoundedness. So if gamma was 1, then you have unconfoundedness. And the technical reason is that if gamma is 1, then like somehow these functions cannot depend on y. So they are only functions of x, so you can construct some covariate space where your probabilities only depend on x and not anything else. That cannot be seen from just this formula. You have to use other properties. So I guess don't try to do that. But you can think of this as some analog of like robust statistics in causal inference, where in robust statistics, what people try to do, and like going back to works of Hooper, is you have a Gaussian, you want to estimate it. Can you still do it if you have gamma fraction of corruptions? And the typical results we show is like, yeah, we can, but we can only output a distribution which is gamma close in TV distance, right? So that's the analog of the results known here as well. We can only identify some interval which is of gamma length where the average gamma minus 1 length where the average treatment effect must lie. Okay. But there are analogs, like the adversarial robustness really wanted to look at the adversarial case where like an adversary is choosing, and there you can obviously not do much more. But in sensitivity analysis, we are also interested in benign cases where like you have some deviation, but maybe it has some structure, right? And maybe there is a feature that you were missing, and that so it's not adversarial, it's just that feature which violates and confoundedness. Maybe you can do something more. So that's the sort of result we prove. So we show that in sensitivity analysis, these frameworks remain identifiable if, for instance, the outcomes given X are some arbitrary function plus Gaussian noise. And Gaussian doesn't need to be there. It can be any other, like Laplacian, whatever, your favorite parametric structure there. But so it's very parametric in the sense we require the noise to be Gaussian or have some specific parametric structure. On the other hand, it's very general in the sense it can have any functional dependence on X. Like I don't want this to be a polynomial or linear function till now. Okay. And why we found this particularly interesting is because this Gaussianity assumption is already used in other parts of the pipeline. So you anyway need this to learn the propensity scores and a bunch of other things. So if you're already assuming this, maybe you will be willing to like eat this assumption to get identifiability as opposed to just an interval estimation. Okay. So now, like I'll try to. Okay, this is all. So I'll try to connect this back to the identification condition, these ratios that we came up with before, and try to convince you that this example works. Okay. So this is a proof of the corollary, I guess, in some sense, if you buy the main result. So formally, I define the scenario as the follows. So the generalized propensity score is bounded between some numbers between 0 and 1. So this can be translated to, the first line can be translated to saying that each cluster is non-empty in both sides. But I don't require anything about unconfoundedness. And the theorem is that this is identifiable for all distributional classes. So this is identifiable for all distributional classes, where for any pair of distributions, there'll be some point where they exit like some bounded interval. So the density ratios of distributions become unbounded at some point. So for instance, if like P by Q looks like a function like this, it exits my interval at like 2 places. So these pair of functions are good for me. The pair of functions which are not good for me are these like this ratio in red, because it always remains between these two intervals. Okay, and the proof of this is not too hard. So recall what we wanted to show is this ratio P by Q as a function, which is the thing I drew, should not be equal to the ratio of two propensity scores. And the only thing I've assumed about propensity scores is they're between C and 1 minus C. So to deduce the corollary, the only thing you have to notice is because P and Q can be any functions with values between C and 1 minus C, arbitrary varying, I can realize any function in red with P and Q, but I cannot realize any function which exists this interval because that's too large of a value when we have this restriction on the propensity score. So it's a simple derivation. And if you go back to Gaussians, if you take ratios of densities of two Gaussians with different means, or different parameters in general, there is some point far enough away where the density ratio will either go to 0 or blow up. It's just because of the fact that there's a polynomial in the exponent. So that already tells you that that's the only property we're using. So if you put in Laplace, this works. If you put in any e to the polynomial, this still continues to work. Okay. So any questions about this? Otherwise, I'll go to the next application. This makes sense. Okay, then I'll go to the next application. So yeah, this is regression discontinuity designs that we have been talking about, so I'll not say too much, except that unconfoundedness holds, but overlap does not. So pictorially, it looks something like this. So let's say the scores were on x-axis. Then there was some threshold after which you had treatment, and before which you didn't have treatment. And people can identify the average treatment effect exactly in this model, provided you have like outcomes which are linear functions of x. So things which I've drawn here. And the rough reason is that like you see data for the solid line here, but not for the dotted region. And similarly, like the data for y0 you see in this range, but not in this range. But by virtue of being linear functions, if you fit this function here, you can extrapolate. And if you fit this function here, you can extrapolate. So that's basically like why people can handle linear functions. One thing I want to mention is like, yeah, they assume linearity, but then for the noise, they don't need to assume a parametric structure. They only need like expected value of the noise to be 0. Yeah, so how do you extrapolate polynomials? If you can, so now identification is not hard, right? People had not written it down, perhaps because they're more interested in estimation, where instead of getting this linear function, you'll get some like slight perturbation of it. And for polynomials, the tricky thing is just to bound this extrapolation ability. So as the degree of the polynomial increases, you need higher and higher, and in a very bad sense, higher and higher accuracy to estimate the polynomial to be able to extrapolate. And so that's why. And okay, and like the existing results were also limited to 1 dimensions because these are results from like 80s. And since then, people have mostly been finding studies where you have like some score, which can eventually be laying down on a real number line. But you can imagine an extension of this. You have an arbitrary feature space. There is some set which you'll give treatment to, and everyone outside that set you will not give treatment to, right? And this can be a very complex set. So this problem makes sense in that regime also. So our results is sort of like exactly the result you were asking for. I'll only state the identifiability result here because estimation is slightly annoying to state. But yeah, you can extrapolate polynomial functions. You can even extrapolate things which are more complicated than polynomials. Here I stated it for like polynomial plus noise where noise is 0. But you can look at other models, like you can look at joint density of x and y, and if it's e to the polynomial sort of form, you can somehow you can extrapolate all of this, right?
Yeah. There are two different polynomials that you T0 and T1,
Yes.
which previously was not the case.
Yeah, it should. That's a typo. There should be a WT here. There's always two functions. Oh wait. No. Sorry. That's right. So they used to look at like one linear function, but it's not hard to extend to the two linear function case. People in the literature mostly look at this one function case because they have some intuition for justifying why the gap should remain constant. Okay, so pictorially speaking, like, yeah, I mean, people used to do this case, we can handle this case, but we can handle this case in higher dimensions also. And here are contributions. I'll not go into them in more detail, is because our contribution is to make the connection between causal inference and this area of extrapolating functions. So this is more recent, like some work in like old work in statistics, but recent work in computer science trying to get efficient algorithms for extrapolation. It's called, the area is called truncated statistics. So our contribution here is just to make this connection and then leverage some results there too. Okay, so now I'll slowly go over like the proof of our identifiability characterization. I'll not go into the quantitative version of it. Before that, I just want to be on the same page about what I mean by identifiable. This is the strongest definition of identifiability I can come up with. Strong in the sense that learner has the most power. So I say the average treatment effect is identifiable for these classes if there is some deterministic way of mapping the density of my sensor distribution. So remember, I see only one y for each person, so that's why I'm calling this sensor. That maps my sensor density to the average treatment effect value. Right? And this works for all distributions which are realizable with respect to my classes. So this is a funny definition in the sense that this function, I allow it to depend on measure zero sets as well, as long as the density there is different. Right? So it's somewhat weird, but like maybe our second result, which is quantitative, addresses this fact. Like somehow the characterization, like this is a, so somehow the characterization we get here naturally strengthens to get you finite sample estimation guarantee as well. Usually in learning theory, you don't have to worry about this because this mapping is obvious. If you are doing binary classification, you have a bunch of data points. This is the Bayes optimal classifier and always exists. Here we have to show the existence of this also. So just to, I guess, maybe make this more clear, another way to phrase this is if you have two distributions, D1, D2, both of which realizable with respect to my classes, and the average treatment effects are different on these two distributions, then their density, sensor densities must also be different. Because if these densities happen to be the same, my deterministic map will return the same value and it will be wrong for at least one of them. Okay, so that's identifiability. And I'll restate my identifiability condition, but now with like some more details. So I say, yeah, so earlier we just had this last condition that for two generalized propensity throws, two densities, the ratios cannot be the same. Now we just want this to, okay, maybe the way to state this as follows. Okay. So at least one of three things should hold for these pairs. Either we get the condition I mentioned before, or we get one of the other two conditions which somehow trivially enable us to like get rid of these bad cases. So roughly what we are trying to do is like among these classes P and D, there is some small p and some capital P which correspond to my actual distribution. And I want to distinguish that small p and capital P from any other small q and capital Q in the classes. Right? So this is the hard condition. But then there are some trivial cases. So let's say if the capital Q and capital Q lead to the same average treatment effect. So this is not quite the average treatment effect, but this implies the average treatment effect is the same. Then I don't really care. Then I don't want to distinguish these two. They lead to my same, either of them will lead to the same value of the average treatment effect. So I'm fine with them. And it's also easy to eliminate pairs of capital Q and capital P where the feature distribution is different. Because if you remember in our setting, there's no censoring on the features. Like you see all the features you like X is defined to be. So I can like easily check this. I can check whether P of X matches my data distribution, Q of X matches my data distribution, and pick the one which matches. Okay. This is the other way to look at it. We say that for any like these two tuples, either their or for any two tuples, if we can verify that their feature distribution is the same, and we can verify that the ratios are the same, then we can conclude that the average treatment effect is the same. Right? So the condition is that these two things together somehow enable us to infer this. This is not always true, but there are classes for which this is not true, but we'll work with classes where this is true. Okay. So let me first prove the easier part of the result, which is sufficiency. So let's assume that the condition that I mentioned holds. And recall that the average treatment effect is the difference of these two expectations. I split up the expectation into two parts. And I'll only talk about sufficiency of estimating the second one, because you can use symmetric techniques to estimate the first one, and then you can take the difference. So we just want to estimate the expected value, identify the expected value of y0, which is why like everywhere I'll have y0 here. Okay. So the first step is like you just recover the density of x and y from your sensor data when t is 0. And I guess the only thing I want you to notice is this is something you can compute from your data. It's literally a statistic of a marginal of your data. And the other thing I want you to note is like I can factor this probability into two parts. One is the probability that I sampled an x and y in my original data distribution. And the second is the probability that for this x and y, t happened to be 0. So it survived in my censored data set. And then, like, if you take the probability of sampling x and y and it showing up in your data set, that's the probability that the density you're looking for. Class D. Okay. Now I do the following thing. I want to look at just candidates P and capital P in my data distribution, which are consistent with this marginal that I have found. So in particular, whatever I'm doing here, I'll go over this. P0 and DXY0 should be in this set. That's the only thing I want to estimate, ensure. And then I check the following two things. This product of P and P, which is exactly this density, should match. And the marginal over X should match. So these are two things I'll ensure, and maybe you already see the answer now, which like we had the second interpretation of our condition, which said that if you have the product being same for two tuples and the marginal over X being the same, then the expected value of Y0 must be the same. And because it's all these things match for every pair of candidates in our class, like all candidates in our class lead to the same value of E of Y0, so it must be the correct value. And you can do the same thing for expectation of Y1 and then compute the average treatment effect. Okay. Any questions here? So for Y1, I'll have T1 and Y1. So like you see Y0 when you have treatment being 0. So like what you see why people smoke when the outcomes when they smoke, when this like the assignment of treatment was smoking. So every like 0 will turn to 1 in the proof. And maybe before going to necessity, I'll just mention quickly what we need for the finite sample estimation of this. So for the finite sample estimation, we need some robust version of the condition, which says that if the products approximately match and the marginals approximately match in TV or your favorite distance metric, then the average treatment effect has to approximately match. And for all of the examples of polynomials I've shown so far, you can get these approximate statements as well. It's just like the exact statements are very easy to prove because the density shoots up. But for that example, to get the approximate statement, you, for instance, have to compute if my parameters are epsilon far away, what is the mass of the set on which the density is large? And then you can only like, as you want more accurate estimation, as epsilon goes to 0, you need to estimate you need to detect difference on a smaller and smaller set. You need more and more samples. So that's all. That's all. Okay. So then, yeah, I'll talk about necessity, but this, like the previous one is almost a formal proof. This won't be a formal proof. So the first thing is to, yeah, I mean, we do the obvious thing. You want to assume that the identification condition fails, and it failing means the following thing. So there are some tuples P and P, Q and Q, which match in X, like same marginal X, same ratios, but the average treatment effects are different. And oops. Yeah, so and we'll use these tuples to create two densities such that I eventually want to get to this, that these censored distributions of D1 and D2 are the same, but their average treatment effects will be different. And I'll partially define D1 and D2 here, not fully. So partially, I want like, I do like the obvious thing where I take X and Y0's distribution as P in one case, Q in the other case. I take the propensity score as P in one case, Q in the other case. And then if you believe, like I've only specified part of the marginal so far. So the thing you have to be careful about is somehow you can define the other marginal while having a consistent distribution. If you want to extend both of these distributions which have different expectations, but you want to be able to do this without affecting these marginals at all. So that's the tricky part. That's where this compatibility clause comes in. I want to describe that here. But if you can do that, then it's like this follows by definition, because the expectations being different is easy. That's just by this clause here. And the sensor distribution being different, being the same is also easy, because in the previous slide, we saw that sensor distribution is somehow the product of these two things. And we set up this distribution here. The product in one case is capital P times small p. The product in the other case is capital Q times small q. And if you take cross products here, you get that result. Oh, wait. This should have been the opposite way around throughout, so that this cross product works. So that's all. That's the necessity proof, and I'll just summarize. So in this work, we presented some learning theory inspired framework for identifying average treatment effects that extends the regimes in which we could identify the average treatment effects before. And there are several interesting directions here. Like one of the key contributions of this work is to draw this connection, right? And this bridge opens up maybe more avenues for how learning theory tools can be used in causal inference. For instance, like, can we have some analog of robust statistics for causal inference, like more than like which can get better bounds or computationally efficient algorithms better than the ones which we currently have. And then there are more specific questions, like we get some estimators, but they rely on the traditional statistics techniques where you construct a cover which is of exponential size, and you pick the element of the cover which is the best fit. These are, needless to say, like not efficient at all in practice. Like, can we have some loss minimization based estimators so that at least in settings where you have efficient loss minimization algorithms, even heuristic ones, you can use those algorithms? Can we, I guess I already mentioned, can we get some form of robustness? And the final thing is like an important aspect of causal inference is actually getting results on real world data. So all of the frameworks or assumptions I mentioned, some of them, like this linearity is inspired by specific studies where they could justify linearity, and that allowed them to infer some causes. Having these more general results, can we actually do some evaluation on real world data and like get inferences in some cases where we couldn't before? Okay. So with that, I'll conclude. Here are the references. Thank you. And happy to take any questions online or offline. Yes. In the agnostic setting, like there's nothing formally known because people haven't taken this learning theory perspective. But I think you can, if you take the like extreme agnostic perspective that we usually take, then you'll very quickly get to a fact that you can only identify average treatment effect up to some additive factor, right? And it's not known whether you can nail down that additive fact. Like can you get off plus epsilon type estimation results? Okay, then I'll stop.
Let's thank Anay and Thank you. We also have lunch outside in the garden. Which was